right, hello my friends. So in this video, I'm going to give an introduction to series. So I'm assuming if you've watched this, you've never heard of what a series is, and sequences and series always come hand in hand. They get surprisingly difficult depending on which class you're, like what the context is, I guess. So a series and these things have a lot of overlap because a series is basically taking a sequence and adding the terms of that sequence. So a series takes a sequence and then just literally adds all those terms that you might list out. So for a series, believe it or not, it gets a little complicated having a series, and we have to use special notation. So that notation is the summation sign. So this is the Greek letter uppercase sigma. And so just whenever you get introduced to a Greek letter in math, like your best practice is to try to really make pretty Greek letters, because it can be very hard to read your work if you don't. So this is an uppercase sigma. It is not this. That makes me sad. So you want to try. It might be kind of hard to draw, but like if you want to really try to make like finer points, it just makes your work more clear. So just a nitpicky thing, but it will make your work more readable, which I think is good in the long run. The summation sign really means add a bunch of stuff. Doesn't matter what class you see it in, pre-calc, statistics, calculus. It has lots of different applications actually where you might see this, and I can't really think of a place where this symbol doesn't mean add a bunch of stuff. There's other times in math where the same letter can count for several different things, but just thinking about this, I can't think of any other place where the sigma sign does not mean add some stuff together. And so this is actually incomplete. There is other stuff that goes along with it. So here's everything that goes with the summation sign. So you could have an I here or a J or a K. So this letter down here doesn't have to be an I, but usually you'll have like an I, and then this N is very often a number. And then this is talking about a sequence that we're going to cycle through. So what this means is sum up all the terms from 1 to n of this sequence. So we'll break all this down. Okay, so this I part here, so like I said, it could be an I, it could be a J, it could be a K. This is what's known as the index. And then this A sub I, this is like a formula, or it could be even something more general. So I'll show you a few examples of like what this can take form as, because we can sum up anything we want, which sounds really simple in theory. And I think it is simple in theory, but you can make a lot of questions that look surprisingly hard. So I want to throw those at you in this video so that you feel very comfortable with this notation. Okay, so that's kind of the overview. And so what this like literally means. So you're cycling through the terms of this sequence. A sub 1 is the first term, A sub 2 is the second term, A sub 3 is the third term, all the way out to the nth term. And this sum sign means add every single one of those terms. So that is in theory what this means. Okay, so we have two types of series. We have a finite series. So finite series has this form, A sub 1 plus A sub 2, all the way out to add up to A sub n. So basically it has a start and a stop point. Okay, so I think a finite series is pretty obvious, as is an infinite series. An infinite series has no end. So when we write it out as a sum, you start from I equals 1 to infinity. So this actually is a whole other can of worms. I mean, you could spend a long time studying infinite series. If you end up going to Calc 2, you spend a long time talking about these things. Like summing up an infinite level of terms, it is surprisingly complicated and very interesting, actually. Well, interesting, I'm a math teacher. What do I know? All right, so let's evaluate the following sums. So just to kind of get you to understand this notation. All right, so I have really low sums here so that we can kind of play around with this. So I'm going to start from I equals 1 to 4. So what does this all mean? We're going to write out this actual sum. So we treat this like a sequence, and we're going to start the sequence at I equals 1. So starting with that first term, I'm going to plug in the 1. So there's my first term of my series, okay? Then I'm going to go to the next one. So now instead of plugging in I equals 1, I'm going to cycle to the next term. Plug in I equals 2. Okay, now what do you think I do next? Plug in I equals 3, and then plug in I equals 4. And this is where I stop. So notice I cycled through a different number each time for I and stopped at 4 because that was the stopping point here. And from here, now this is just a matter of us doing the math. So we can just calculate all these separate terms and then add it up. So it's 124. So it's literally just adding stuff up together, but it's kind of like a complicated way to do it, I guess. Okay, so here's like a nice straightforward example with numbers. But like I said, summations can really count for like whatever you want. So I want to throw a couple of weird looking sums at you. So like I said, you don't have to use I for this. You could use like a J for this. So check this out. This is a series that's going to start at J equals 3, and we're going to go out to 6. And I don't know, I don't have a formula for this. So I have to just work with what I've got. So where I see the J, that is the only part of this formula that's going to cycle through. So I'm going to cycle through from J equals 3 to J equals 6. There's nothing I can do with this A. So I'm just going to leave it alone. I'm just going to let it chill. So I'm going to start with A sub 3, A sub 4, A sub 5, and A sub 6. That's it. That's all I can do. I can't even add this up any farther. But that's what this series wanted me to do. So that's me writing it out. Okay, so now let's get to, like I said, like the thing with series is it's a really simple idea, right? Like this example seems very simple. This one is actually also pretty simple, but it looks very complicated. And it's a little more complicated because it has double layers to it. So what we're being told is to cycle through from K equals 1 to 4. So notice I changed this letter from I to K because it doesn't matter what letter you have down here. So what I'm going to do is first I'm just going to set up this sequence, or sorry, I'm going to set up this series, and then I'm going to worry about this information next. So first let's just evaluate what it means to go from K equals 1 to 4. So this is going to be 4 x sub 1 minus 1. So that's me plugging in K equals 1 here. I'm not going to worry about this detail right now. I just want to set up what does this part here mean. Okay, so that's the first part. Then we're going to cycle through to 4 x sub 2 minus 1, and then 4 x sub 3 minus 1, and 4 x sub 4 minus 1. And now I have completed what the series wanted me to do, right? However, these weird terms, x sub 1, x sub 2, x sub 3, x sub 4, this second layer of this problem is telling me what inputs to use for those. So where I have an x equals 1, now I'm going to replace that with a 2. So this becomes 4 times 2 minus 1. And then for this next one, so where I have x sub 2, I'm going to replace that with a 3. Times 3 minus 1. And then where I have x sub 3, I'm going to replace it with 5. So you're not worried about how they got these numbers. That doesn't actually matter to us. We are just going with the information that we are given, so we know how to write this out, and now we're just told to use these, and we're not going to think any deeper about it. So for my last part here, this is going to be 4 times, well, where I had an x sub 4, now I'm going to replace it with an 8. And then it's the same thing. So then I can just do the math here. So let's see. This is going to give me 7 plus 11 plus 19 plus 31. So this sum has a value of 68. So sometimes you can have, so if we just refer back to the last example for a second, we couldn't go any farther with this. We just didn't have any information. So this is a possibility. But in this formula, so we started out with these theoretical x's, and then we had a second layer of what to put in for them. So it's totally just dependent on the sum. So you've just got to kind of watch out for it. All right. So let me give you one really wild looking one. I know we're getting towards the end of the semester, but we've got to still have fun, right? This is fun, right? Okay, so what I want you to do, I know there's like several layers here. So I want you to try this one on your own. So if you're totally stuck, I'll walk you through the pieces. So without worrying about what all of these things mean first, just write out how to like set up and evaluate this series. So you write that out and then you hit play and I'll show you. Okay, so this series, if I just set it up, I'm gonna start with x sub 1. I don't know what this delta x is, so I'm not gonna worry about it. The only thing I need to cycle through are where I have these i's here, right? So I'm just going to continue on with these x. And by the way, if you weren't aware, I said the name, but maybe not everybody knows it. This is not triangle x. The way that we read this is also a Greek letter. Yes, there's a Greek letter that looks like a triangle. This is called the letter delta. The farther you get into math, the more you learn about the Greek alphabet. So this is delta. So we call this delta x. Okay, so look at this formula now. So I think you can figure this out if you're stuck, but I will give you some like things to think about. So notice that we're told what the function is, and then for each different x value, we're told what to plug in. And also, look, we have delta x just equals 3. So you have all the pieces that you need to evaluate this. So I think this would be a good time to challenge yourself. Pause here and see how far you can get with this and see if you can get the answer. Hit play when you're ready. Okay, so what I'm going to do is f of x equals 3x. So if I'm going to take f of x sub 1, I'm going to take 3 times x sub 1, which is going to be just 1. So everything that goes into this is going to be 3 times 1, and then my delta x is going to be equal to 3. So if that just gave you whiplash, so my f, I used this part here, so that's this 3. My x sub 1, I referred to up here, so that's what I plugged in here. And then finally, the delta x was here, so that's what I replaced here. That's why this is a 3. So those are all the pieces. So if you want to pause and just kind of like acclimate your eyes to that so that your brain gets it, I would do that before you move on. Okay, so now, let's keep going. So now I'm going to take that 3x and I'm going to plug in for that one. So f of x sub 2, so plug in 4 for that. 3 times 4, and then the delta x was just 3, so that's all times 3. And then this last one, I'm going to take f of x sub 3, so I'm going to plug in 7. This becomes 3 times 7, 3 times 7 times 3. Okay, so I put these together just so that we could tell this is part of the function, and then that times 3 is the delta x part. So now it's just a matter of just multiplying everything together. So this is going to be, let's see, this is 9 and 36, and let's see, 21, so this will be 63. Okay, so I got all the pieces there, so if I add those up, this comes out to 108. So like I said, so these series, they can start to look kind of wild. So I wanted to show you all those because this actually is a very powerful tool depending on what you're doing with math. You might not know what all this means, but in a later math class, understanding this notation is very key. Now, what if we have larger sums? Because we've just been dealing with 4 or 5 term sums. The real power of a series is that you can add up, say, 100 or 1,000 terms together. And to do that, for these larger sums, we have handy properties. So I'll just show them to you. So we have the summation properties. So we're going to let a sub n and b sub n, these are going to be 2 sequences, and c is going to be a constant. So let's say that I'm trying to sum up some constant series. So this is just a number. Pretend like this is 7 or something. If I wanted to sum up the terms from I equals 1 to n, I just take n times that constant, and that will give me the answer for that, or that will give me the sum of that series. Next, if I have some summation from 1 to n of a constant times that sequence, you can actually just factor the constant out of this and focus just on the figuring out the terms of your series. This is really handy, and I'll show you why in a few minutes. You can also break up 2 series that are being added together. You can break them up into separate series like you see here. And also, if you have two series that are being subtracted, you can break these into two separate series. So here's one sequence minus another. I can separate these into two separate series. Okay, so these are handy rules, and then I'm going to show you these like insanely handy rules. Okay, so we have these summation rules. So what if I wanted to sum up the terms from 1 to n of just the sequence I? So think of how this sequence would look. This would cycle through as 1 plus 2 plus 3 plus all the way up to plus n. So n can be any number that you want. It could be 732. So if I asked you to sum up 1 plus 2 plus 3 plus 4 all the way out to 732, you'd probably be mad at me. But we don't have to do that. We have a formula for that, where all I have to do is take whatever this last number is and plug it in here. And that gives me the result of the sum without having to add up all the terms separately. So I'll show you how to use these in a few minutes. If I have a bunch of squared terms, so what this would look like, so I have I squared here. So think of this as like 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. If I wanted to sum those up, I can use this formula versus me having to like sit there and actually sum them all up. So again, I'll show you why this is handy. And then finally, we also have a formula for cubes. So if I have like 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way out to n cubed, I can cut all that work down by just entering it into this formula. So whatever number is up here is going to drive the calculations in these formulas. And don't worry, I would say just write these down and we'll just use them so that it makes sense. So let's evaluate some sums. Okay, so here's like that first one I was talking about. So I want to sum up from 1 to 50, just the constant 3. So first of all, what this looks like, the first term here would be 3. The next term would be 3. The next term would be 3. There's no I in this formula. You see, it's just 3. So what that means is that I'm just going to add 3 together a total of 50 times. So we're going to do this, add this 50 times. And so that's what this rule over here is getting at. If you have a constant here, you can just take n times that constant. So if I come back to this, my n here is 50. So I can actually just write this as 50 times 3. So the sum of this would be 150. Okay, so up next, I want to do, how would I sum up k equals 1 to 25 of 3k? All right, so this is now where some of those handy formulas are going to come into play. So one thing I want to use here is, this constant rule. So I have a constant, I can actually factor it out of the sum, and I want to do that. So if you're not sure why, I think it'll make sense in a second, so just kind of go with me here for a moment. So I'm going to factor out the 3 like so. Okay, so notice now I'm just left with summing up the plain old terms k from 1 to 25. So if you think about what that would look like, I would have to sit here and write 1 plus 2 plus 3, and I would have to do that all the way to 25. Now, while we could do that, it would take a little while to like do all of this. So we're going to save some work and we're going to use the formula. So the formula is right here. We're just summing up the terms. Remember, I can use I, J, or K, so I purposely switched it to K just to kind of get you to think about this in different ways. Since I'm just summing up all those terms from 1 to 25, I can use this formula here. So where there's an n, I'm now going to replace it with a 25. So this is going to be 3 times 25 times 25 plus 1 divided by 2. So I can do this calculation. So I can take 3 times 25 times 26 and then divide that by 2 to get 975. So that's the value of this sum. And this was a lot faster to calculate, right, than sitting there trying to add up 25 different terms. Okay, so I want to do one more of these. So I'm going to go from now j equals 1 to 33. So now I've got 4j squared plus 1. Okay, so I kind of showed you like how to set this up. I'll give you a hint that you are going to want to break this into two separate series. So I would challenge you to like spend a moment just trying this on your own and like staring at your own sum formulas and like giving your brain a chance to try to digest this and see if you can do this totally on your own. And there's no, there's no problem if you don't get it on your own. It gives you like, it'll make this more meaningful if you spend some time doing that. So go ahead, hit pause, hit play when you're ready. Okay. So if we're looking at the rules here and see, look, it's hard to make nice summation symbols. When I am drawing them a lot, then my summation signs are like straight fire. And then when I take a break from it, they just start to look sloppy again. Like this is, what am I even doing? I should just stop and quit my job. This is terrible. Okay, maybe I'm a little hard on myself. Okay, so I'm breaking this up into 2 separate series. And then I want to, and I forgot the squared. Okay, so this series now I can evaluate. This will just be 33 times 1. This one I can almost evaluate because remember, I have a formula for the term squared. So I can use this formula right here for this. So if you weren't sure where to start, like hopefully this kind of like kickstarts you. So maybe pause and try. So what I can do is I can factor out that constant. And then I'm just going to write this second sum as 33 times 1. Okay, so now I can use the formula here. So this is going to be 4 times, just to reference that formula. So where I have an n, I'm going to replace it with that 33 all into this. So this is going to be 33 times 33 plus 1, and then 2 times 33 plus 1. All of that divided by 6. And then all of that plus 33. Okay. So don't forget that we still have this calculation at the end here, so you have to have this plus 33. Okay, so I'm going to have 4 times 33 times 34 times, let's see, 67 divided by 6 plus 33. So this comes out to 50,149. I would have hated to have to calculate all of these terms from 1 to 33, and this is a huge sum, so this was actually a pretty nice way to go about this. Okay, so that is your intro to working with series, so hopefully that was helpful, and I will catch you guys in another video. Thanks for watching.